So today's lesson is about telescopes, which of course is the major tool for all astronomers. The biggest lesson that I want you to learn about telescopes is they are tools that we use for gathering light. In fact, I think your text refers to a term that you should embrace. Telescopes are light buckets because that is the basic purpose of a telescope, is to gather as much light as possible. This actually allows us to get more information about whatever we're looking at, whether it be a galaxy, a planet, a star, a nebular cloud. We want to gather as much light as possible, and telescopes are the tool. Here are some pictures of different types of telescopes so you can broaden your thought about what you think about when you see a telescope. In the upper left-hand corner, you might see a telescope that you might be able to own. You might go to a store and buy this telescope and use it in your backyard. In the upper right-hand corner, we see the type of telescope that would be, launched in the sky by scientists. In the lower left-hand corner, we see radio telescopes, which really look like big satellite dishes, which is essentially what they are. And then finally, in the lower right-hand corner, we see a large research telescope, which is made up of a very large mirror, and it might not be obvious to you, but it is located on the top of a mountain somewhere, and we will learn later why that would be the great place to put that telescope. So what is the main purpose of telescopes? Well, I think I already spoiled that surprise. The main purpose of a telescope is to gather light. If you think about it, when you look into the sky, you might realize that you can see some stars, and some stars are brighter than others. If you ever had the opportunity to view the sky through a telescope, you might notice that you can see a lot more stars through the telescope than you could with your naked eye. And that is simply because your eye clears the image, your brain clears the image every fraction of a second, so your eye is only collecting light for a certain amount of time. If a star is not bright enough to sort of make an impression or to signal your nerves in your eye that it's there, you don't see it. But with the telescope or even simple binoculars, you can gather enough light so that you can actually view the object. So telescopes help us view dim objects, which is going to allow us to look farther into the sky. And remember, that also can mean deeper into the past. So, do we just use telescopes to view things that we could see with our naked eye? That would be the visible portion of the electromagnetic spectrum. Is that true or false? It's actually false. We're going to see that there are many different types of telescopes that allow us to view different types of light waves, such as radio waves, X-rays, ultraviolet rays, because in putting all those pieces of the puzzle together, an astronomer can get a more complete picture of what is going on in our universe. So, do you think that when building telescopes, the main rule of thumb is bigger is better? Is that true? Well, you might be happy to know that, yes, bigger is better. The bigger the telescope, the better image that we're going to be able to get, and we'll see why that's true. So let's just talk a little bit about your eye and how it works, because that might help us as we're looking at telescopes and thinking about how they look as well. In these pictures here, at the bottom you see our eye, and you know probably that your eye has a lens in it. And at the back of your eye is where your retina is. And this is where images should be focused so that the nerves in your back of your eye can send a message to your brain to let you know what you're looking at. What they're showing right here is the light coming into the lens is being focused, so all these light rays come together right at the back of the eye, and that's the perfect scenario. If you wear glasses, the sad fact is that the focusing is probably either happening in front of your retina or in back of your retina, and your corrective lenses help to move that focal point right to the back of your retina so that you can see better. In this picture here, this is more like is the scenario for something that we're viewing that's very far away, and that's why the light rays are coming in parallel. Here we're seeing a dog, and we want to sort of think about how the image of the dog is processed by your eye. We imagine certain light rays coming off of the dog at certain points, and where those light rays end up once they pass through your lens is where, say, here these light rays came from the tip of his head, and that's where the image of the tip of his head ending up after the light passes through the lens. Notice that your eye inverts the image, and we'll see that telescopes do that as well. You might, if you've ever had the opportunity to view, say, the moon through a telescope, you might have actually caught on to that the image that you're viewing through the telescope is actually upside down from what you actually see in the sky. So there are two main types of telescopes. The first telescope is shown right here, and this is the main part of it has a mirror, and so it's called a reflecting telescope, or sometimes just referred to as a reflector. In this telescope, the main part of it is a lens instead of a mirror, and so that is called a refracting telescope or a refractor. So when we're talking about telescopes that we're using to view visible light, those are the two main types of telescopes that astronomers use. A refracting telescope, that was the second one that you saw on the previous slide, has the main part of it is a lens. So a lens allows light to travel through it, but it has a special curvature that focuses the light rays exactly as we want them to be. And so the reason it's called a refracting telescope is that the phenomena that it is using of light is called refraction. It's actually using the fact that light refracts when it passes through the lens. So we might not be familiar with refraction, so let's see what we're talking about. Refraction is the bending of light as it passes from one material into another. So let's talk about why it does refract. So we're talking about, you know, if light goes from, say, glass into air, or from air into water, when it's going from one material into another. So light refracts because when light goes from one point to another using the principle of least time, it takes the quickest path. So we're familiar with the idea that the shortest distance between 2 points is a straight line. It turns out that for light, the straight line is not necessarily the quickest path in terms of the amount of time that it's going to take. And so light will not necessarily choose a straight path, but it's going to choose the quickest path. It turns out that that quickest path will turn out to be crooked, which means that's why the light ends up bending, to take that quick, crooked path. And the reason for this is because when light goes into different materials, it actually changes speed. We're familiar with the idea that light travels at the speed of light, the 300,000 kilometers per second. It turns out that that's only true in a vacuum. So when light goes into water, it slows down. When light goes into glass, it slows down. And so that's something to take into account. So when the light's going from one material into another, it's actually changing speed. And so because of those two things factored together, light actually bends so it can go from one material into another, so it goes more quickly. So an analogy here is rolling a barrel on concrete and then running into the grass. And notice this barrel is traveling at an angle. So these concrete and grass is sort of taking the place of two different materials that light might travel in. And so as the barrel is rolling along, of course, it's going to be easier to roll it on the concrete than the grass. So we would say that it's traveling faster on the concrete. But when it hits the grass, it's going to slow down. And so this end is going to hit the grass first, and it's going to slow down, but it's only going to slow that part of the barrel down, and the rest of the barrel is going to kind of pivot around that point and then continue on in a different line. Notice that when it hits the grass, it goes in a different line. It has bent. Similarly, when light hits the boundary between two materials, it's going to change speed, it's going to cause sort of a shifting in the direction, and that's the refraction. Here's a picture of a refracting telescope. Notice where the placement of the lens is going to be up near the top of it, and then there'll be another eyepiece that is actually going to sort of refocus the image, which would end up being right in here, so that someone standing down here could view it. It turns out that when you learn about really high-tech telescopes, you're going to find out that they're not refracting telescopes. There's a couple different problems with refracting telescopes. It doesn't make them bad, it just puts some limitations on their uses. For two things are that the lenses absorb light, and if you're trying to collect as much light as possible, this ends up being an issue, where for a mirror, it's going to just reflect the light, so we're not going to lose any of the light we're trying to gather. Lenses, when they get very big, of course, are going to be very heavy, and the curvature of the lens is quite important, so because it helps it focus the light properly. And so if it's really heavy and I can only support it around the edges, it'll tend to sag, and that can affect the quality of the image because of the sagging and the distortion of the lens. And finally, refracting lenses also have something called chromatic aberration, which we can show here, which is basically the fact that different wavelengths of light will bend different amounts when they go through the lens. So the two ends of the visible light, remember, we refer to as the blue and the red, and the blue end actually bends a little bit more than the red, and so they don't focus at the same location. And so what that ends up causing is sort of halos of different colors around your image. You can introduce a corrective lens to sort of compensate for that. Of course, then the disadvantage of that is that the lens, you're absorbing more light. So now we list these disadvantages for refracting telescopes, and again, it doesn't mean that nobody wants refracting telescopes. You can get a very nice one that can give you, beautiful images. It just helps to understand why we haven't created huge refracting telescopes for use by astronomers. We're going to start with reflecting telescopes in the next video, so we'll stop here.